For our final project, our group wanted to investigate the relation between the number of leaflets and stress and strain distributions of the aortic valve. The 4 heart valves play a crucial role in the cardiovascular system. At the start of each heartbeat, blood returning from the lungs and body enter the right and left atria. As the blood builds up, the tricuspid and mitral valves eventually open to let blood flow into the right and left ventricles. After a brief delay, they close to prevent backflow. The ventricles then contract to pump blood through the pulmonary and aortic valves, which lead to the lungs and body, respectively. There exist 3 major complications associated with heart valves. Regurgitation or backflow occurs if a valve doesn't close tightly enough, causing backwards leakage. Regurgitation is most often due to prolapse, which occurs when the leaflets bend backwards. Stenosis occurs when a valve's leaflets thicken or fuse together, and atresia occurs if the valve lacks an opening for blood to pass through. Currently, diseased valves are replaced mostly by mechanical or bioprosthetic valves. These valves, however, have several limitations. For example, mechanical valves require lifelong anticoagulation therapy to prevent thromboembolism, and bioprosthetic valves have a limited durability. Most importantly, both valve substitutes cannot grow, repair, and remodel over a patient's life, resulting in multiple surgical interventions. Tissue engineering presents a promising opportunity to create living autologous valves that respond to changing cardiovascular environments. Our project investigates how varying the number of leaflets affects aortic heart valve performance under diastolic pressure by 3D modeling and simulation.
A computer model for each heart valve was generated in SolidWorks before importing into COMSOL. First, a guide curve, roughly cup-shaped to mimic leaflet curvature, was created. Planes were then generated along the guide curve before boomerang shapes were sketched in each plane. These shapes incorporated some values from literature. For example, the leaflets were designed to be 1.5 millimeter thick. The loft feature was then used to connect each cross-section to form one leaflet, which was then used to generate a circular array around a central axis. Finally, a thin-walled cylinder was extruded to form a vessel wall around this completed heart valve. In COMSOL, we selected the 3D model, solid mechanics, and stationary study options before importing the SolidWorks part file into the geometry node. Assuming simplified isotropic valve behavior, the radial Young's modulus and Poisson's ratio were input in the materials node. The vessel openings parallel to the annulus plane were fixed to keep the valve in place for the applied load, and a transvalvular diastolic pressure was input on the interior of the leaflet's cup shape and adjacent vessel wall. Finally, a free tetrahedral mesh was formed and refined once before the stationary study was computed.
When we run COMSOL under the parameters described, we see that the majority of the stresses lies at the interface of the leaflets and on the edges. This quality holds true for the different valve models, as seen here in the tricuspid model. You may have also noted that as the number of leaflets increases, the maximum stress values decrease. This is confirmed by studying the quadricuspid model, which has the lowest value for maximum stress among the different models. Now looking at our strain distributions, we see similar trends to those of our stress distributions. The majority of the strain occurs at the leaflet interface and at the edges. Just as in the stress distribution, we see a decrease in the maximum strain as we increase the number of leaflets in our model. The quadricuspid model has the lowest maximum strain among our models. Seen here is a graph depicting the decrease in the maximum strain with increasing number of leaflets. Evidently, the maximum strain decreases as the leaflet number increases. The red line at the top of the graph depicts the maximum strain cardiac tissue can withstand before tearing, and the graph shows that this is well below the maximum strain felt during diastole. Looking at a similar graph depicting maximum stress, we again see a trend of decreasing stress with increasing leaflet number. The red line here represents the maximum stress cardiac tissue can withstand. According to our models, bicuspid and tricuspid valves will rupture under diastolic pressure. This discrepancy will be discussed next.
Our model has a number of limitations preventing us from making definite statements about the operation of natural heart valves. In order to keep the range of our stress values reasonable, we use the leaflet thickness of 1.5 millimeters. In general literature, leaflet walls are 0.5 millimeters, and it is visible from our models the significant volume of the leaflets. We use Lehigh assumptions, but the valve is not isotropic with different radial and circumferential components. Furthermore, the stress-strain distribution is well known to be nonlinear. Along with these are material properties. The aortic wall does not have the same properties as the leaflets, though we modeled it with the same material. In addition, the body has different structures for reducing stress on the heart valve, including the sinus of Valsalva. Finally, though much of our stress occurs at the leaflet interfaces, our modeling of these interfaces as sharp continuities is non-physical. See that the image has much smoother interfaces. The combination of these discrepancies makes it plausible that the true maximal stresses would be different from the ones our model determined. However, to determine why stress decreases with leaflet number in our model, we posit several explanations. Due to fixed leaflet thickness, as there are more leaflets, the thickness at the central interface of the leaflets increases, which may result in a better distribution of the stress. Second, the length of the interfaces for heart valves increases with the number of leaflets. That is, the amount of contact between the leaflets and each other and the leaflets in the wall is greater. Since the maximal stress distributions are concentrated at these interfaces, this may result in better distribution of the stress as well. Finally, the smaller distance between the leaflets as the number of leaflets increases allows more exaggerated bulging, which causes the interfaces to be less discontinuous, which results in better contact and lower stress. The result from our model may collaborate with literature. In literature, 9 to 24% of aortic stenosis patients have bicuspid heart valve, even though bicuspid heart valve only has a 1 to 2% incidence in the general population. This disease results from the thickening of the leaflets, which in turn could be the result of higher stresses experienced from geometry. Furthermore, although quadricuspid heart valve is rare, it also possesses greatly increased incidence of heart valve anomalies. It only makes up 0.01% of the population, but has about 1% incidence. Some future steps we would like to take are modeling the valves with greater exactness. Some studies give parameters on the design of the aortic heart valve, and while our model is inspired by these studies, it does not have the same geometry nor account for the same range of geometries that a true heart valve can take. We would also like to model heart valves physically. Due to the advantages of 3D printing, we are able to create physical copies of heart valves, which we can put in flow chambers for stress testing. Finally, we would like to observe the long-term effects of heart valves, such as changes in the tissue based on altering the number of leaflets. In conclusion, our study observes some interesting phenomena, and it forms a first step in studying leaflet number as a parameter in the design of artificial heart valves and understanding natural heart valves.